We're good.
All right, so welcome. This is going to be your radio frequency fundamentals for wireless networking, right? The foundation of everything about this course, okay? So, real quick, how many of y'all use Wi-Fi?
Yes.
All hands, right? It doesn't matter. Everybody uses Wi-Fi. All right, how many of you have had your Wi-Fi signal become so degraded it can't be used?
Yes, sir.
Yep.
Everybody, right? You walk far enough away from the building, go 2 rooms down, all of a sudden the thing doesn't work anymore, right? Why does that happen? That's what we're here to kind of discuss, right? Explain why exactly this happens. Maybe it's because the building wasn't configured right. Maybe somebody here in this place doesn't know how to install wireless really. That's what you're going to be able to do by the time we finish, okay? All right, so like I said, the lesson is a foundation for the entire wireless class. Everything about this class is going to be the basic principles to understand how to troubleshoot any wireless network. Being able to understand the core concepts and theory will support wireless will allow you to troubleshoot any wireless network, regardless of brand. While we are going to use Unify in here, right, I'm going to teach you the principles that go beyond Unify. I want you to be able to troubleshoot any wireless network, doesn't matter. So do you all remember my little motto when it comes to theory? No? Come on now, thriving on theory, right? Thriving on theory. My whole outlook is if you understand something at the most basic principle level, you can troubleshoot any system regarding that, right? All right, so today, learning objectives: describe RF signal characteristics, explain the RF behaviors and signal propagation, understand how to detect RF signal factors, and create basic RF channel plans. What do you know? Okay, so let's see. What atmospheric and environmental effects do you expect to see impact your Wi-Fi networks? What kind of stuff? What kind of environmental, maybe facility?
Microwave?
Microwave, right?
Noise.
Something transmitting the same frequency? Yeah.
Noise.
Noise from anything, right? Is 2.4 gigahertz pretty convoluted?
Yeah.
Oh yeah, we talked about that before, right? As you mentioned, microwave, Bluetooth, Zigbee, whatever, right? So many things broadcast on 2.4 gigahertz, right? What about walls,
Walls.
right?
Yep.
The floor, right? If you just have an access point downstairs, are we gonna probably be able to hear it up here?
Probably not.
Probably not that one, right? All right, what would be the biggest impact on wireless communications? In your opinion, this is an opinion one.
Noise. Just general noise from a bunch of APs or a bunch of phones trying to talk
Right.
to the same one.
If we were broadcasting what we do now 30 years ago, there probably wouldn't be near as much noise, but today, there's noise everywhere.
Access point placement?
Yeah, placement, right? So how spaced out are they? Exactly. What about 2.4 and 5 gigahertz? What's the big characteristic differences between them?
They don't interfere with each other.
They're not going to interfere with each other. What about propagation through a space?
2.4 is better, but 5 has better communication.
So 5's got better bandwidth or data rate, right? 2.4, lower frequencies are able to go through walls a little easier, right? So we've talked about that in systems maintenance quite a bit as far as how to use each of them, right? So at 5 gigahertz, you generally want whatever device you have that wants that higher bandwidth closer to the access point, right? All right, radio frequency waves used in a wide range of communications, including radio, television, everything, right? Everything uses wireless nowadays. Satellite communications, RF is a term used as a reference, right? When we're talking about 802.11, we're talking about RF, radio frequency waves, or electromagnetic waves, right? We've talked about that previously in fiber, everywhere else, right? Through the entire time we've been going through the pipeline here. 802.11 networks range from 700 megahertz all the way to 60 gigahertz. That's a huge range. That's a monstrous range, right? Most use 2.4 and 5, and now what?
6.
And 6 gigahertz, right? All right, RF carrier used to modulate data modulation, right? We're going to talk about these terms a little bit more. Modulation is a process used to manipulate a medium. Amplitude is how big that signal gets. Yeah, we're going to talk about that. Phase, in order to change the binary data, right? So that's how we send binary data on an RF wave, is we change the characteristics of the wave a little bit. FCC regulates allocating frequencies, right? Anything that deals with anything being transmitted, FCC is involved. ETSI is the version of FCC in Europe. Any questions about that?
Nope.
All right, next, moving on to wavelength. All right, so when we look at an RF wave, it oscillates, right? It's an AC wave. We learned about AC and DC power. Well, when we talk about carrier waves, stuff like that, it's another oscillating wave, right? So wavelength, right, is talking about the length of one cycle. So the example here is we got 2.437 gigahertz, right? If you actually calculate that down, that wave will travel about 4.83 or 4.85 inches in the space or in the time that it takes to do one cycle. How fast is this wave moving?
Very. Speed of light?
Speed of light. How fast is the speed of light?
3
You're on it.
Very fast.
3.
billion?
No.
No, wait.
Wait.
100,000
300,000
miles per hour? Kilometers per hour.
Meters.
kilometers a second.
Second, yeah.
Close, right? 300,000 kilometers a second. So that wave's traveling that fast, cycling fast enough that it only travels 4.85 inches, right, for that frequency. All right, so wavelength defined as a distance the electromagnetic wave would travel in the time that it would take to do one cycle. So how many miles per second does that? Can you take a venture guess?
No.
186,000 miles per second, right? That's the difference between kilometers and miles. All right, so we have the lower frequency and higher frequencies here, right? We're just talking about the time it takes. So if you increase the frequency, the wavelength does what? What does it do? What does the
Increase.
wavelength do as the frequency goes up?
It increases. Oh wait, as it goes up.
Yeah, as the
wavelength
frequency goes higher,
Decreases.
decreases.
right? That wavelength decreases, right? Because it's cycling faster, so it's going to cycle in a shorter distance over space, right? So here we go. Frequency. Frequency is the number of times complete cycles occur in 1 second. How do we measure that? What do we measure that in?
Hertz.
In hertz, right? So we're talking about 2.4 gigahertz. How many cycles is that per second?
1,000 hertz?
Up, right?
Yeah.
Because we go from, in the decimal system, we go from
Hertz.
the hundreds, right, to kilo, to mega,
Oh.
to giga, right? So you're talking billion, right?
So-
2.4 billion times a second. That's fast.
Fast.
That is really fast. And that's not even really a extremely high frequency, right? That's kind of a mid-range frequency. So those things are cycling quick. So hertz is one of those terms you do want to remember, okay? Here we're talking about amplitude, how big or small that signal gets, right? How much power is behind it. The more power you have behind it, the larger the signal is. Less power, the smaller it is, right? The further the signal goes away, the smaller it's going to get. So that's your amplitude. Amplitude is one of the things we can do to an RF wave to signify data, right? So we have that carrier wave going, we amplify data and bring it back down. That signifies a 1, right? So that's one way we can send data on a carrier wave. Next, we got phase relationship, right? You can take that carrier signal and shift it and then shift it back, all right? It's actually shift the phase of that AC signal. That could be another bit, right? When we're talking about binary, now we can send multiple bits on one shift. We can change the amplitude and the phase and send multiple bits in one change. So this is dictated in a 360 degrees. So right here you can see it is 100, actually this one here is about 90 degrees off phase. Okay, so the entire way around, this can be at 90 degrees out of phase. What would happen if it was completely opposite of each other? What would that be? So if this one started here and went up, and they were basically, when this one's all the way down, this one's all the way up, what degree would that be?
360. No.
Not quite.
180.
180, right? 180 degrees out of phase means that it's going to be the exact opposite of that original signal. Exactly. All right, RF channels, radio frequency divided into bands, right? So what were those bands we talked about using?
1,611? Or 2.4?
Well, not the channels, the bands themselves, right? So
Oh.
we had the 2.4, the 5, and the 6,
Oh,
right?
okay.
Those are the bands. And then the channels, right? So what 3 primary channels do we use for 2.4?
1,6 and 11?
1611.
1, 6, and 11. Why?
Because they're non-overlapping. They don't interfere with one another.
Right? Non-overlapping, they're not going to interfere with each other. Coverage and capacity, two very important things to think of when you're actually getting your Wi-Fi up, right? How are you covering the area you need to? And then capacity, what are you using it for? How many people are you going to supply this connectivity to, right? How much bandwidth does each of them, or do each of them need? So that's kind of what we're talking about here, right? Two factors: coverage, radio frequency area serviced by an access point, and the number of users and devices. It's an example of our coverage area, right? This size of an area, this looks like an office space of sorts, centrally located with one access point. You got the size of area, right? So depending on many factors, size of area, applications in use, obstacles, cubicles, file racks, you think filing rack could potentially block some of the signal and stuff like that? Yeah, so if you've got these, like, essentially a lot of filing cabinets that are maybe blocking on this side of an access point, sure. People on the other side may not get full signal, right? So kind of take the entire space into consideration that you're trying to cover. Capacity, we just kind of mentioned it, right? The definition of capacity is the maximum amount that can be received or contained. What kind of software are you using? Desired throughput performance, channel reuse, co-location, right? So are you using all channels 1, 6, and 11 because of how close the access points are, right? And network aggregate bandwidth. How much bandwidth can you actually provide them? If I've got 1 gig to my access point, and I want to make sure that every user in that area has at least 100 megahertz, how many am I capped? How many clients would I be capped to?
Can you say that again real quick?
So say I had 1 gig of connection to an access point, and I wanted to make sure that each client had at least 100 megs of bandwidth.
Oh, 10?
10, right? I would want to make sure I stop at 10 clients if that was my cutoff. Hey, everybody needs a great connection. Let's cap it off so that nothing else can join that network, right? What's wrong with this picture?
A lot of overlapping on channel 1.
Channel 1 is all sorts of overlapped, right? That is not a great setup, right? So that's going to be co-channel interference because they're all on the same exact channel. Okay, should be deployed in non-overlapping channels to utilize or cover your space. Exactly, great answer. Interference from radius, co-channel, adjacent channel. The only difference between adjacent channel and co-channel, right? It's the reason we use 1, 6, and 11, right? If you use channel 2 right next to channel 1, you might as well just have 2 channel 1s, right? They're overlapping so much as an adjacent channel that you're going to still interfere with the other network. This is kind of showing exactly what we just talked about. 2.4, here we got channel 4 and 6, and we're overlapping about half of that spectrum there for each of those. All right, environmental behavior. We got reflection, right? We talked about reflection in fiber optics. Okay, occurs when an RF signal bounces off of a smooth, non-absorptive surface. You've got refraction, when an RF signal gets bent. Anybody remember what it was called when it bends? What causes that bending from fiber optics?
Oh, jeez.
You remember that? Changing densities. What is that density difference called?
No, I
The
don't.
refractive
been a
index,
second.
right? The density,
Oh, okay.
refractive index, different. A higher refractive index is causing that to bend that light, essentially, right? You've got diffraction. Okay, that's just when the signal basically, when it hits a building, it doesn't really go through it, but it gets bent around that building, so it'll diffract that signal. Different than refraction. You've got scattering, so you're hitting a very uneven surface. Right? You got your signal coming in, hitting a bunch of these buildings, they're all different sizes, and because of it, they're reflecting in different directions off of it. Similar again in fiber optics when we talked about having something that was an impurity in the fiber, right, and that light hits it and it scatters that light essentially, right? Similar concept, right? When it hits something that's uneven, it makes it go in different directions. Attenuation, loss, right? So weakening of an RF wave as it travels along an RF cable through space, obstacles, or through free space, goes through a wall. The wall is going to absorb some of the material or some of the wave, right? And then it's going to dissipate. This is kind of showing that same exact thing. We have absorption, right? As the signal enters this box, decreases out. Next thing you know, you got nothing left. Highly absorbed. What kind of materials do you think of they're highly absorbable to RF?
Metal.
Metal is going to be more reflective.
Oh, yeah.
Right?
Oh, absorbent.
Yeah. Nothing?
What are Faraday cages made of again?
Faraday cage could, right? Because it's going to block it. It's going to filter it. Yeah, that's a good example. Graphite, stuff like that, lead,
Plastic?
right? What's that?
Would plastic be that?
Nah, I mean, it depends on the type of plastic, thickness of the plastic, stuff like that. But
Gotcha.
all right, and then you got diffusion. RF signal naturally widens as it leaves space. So this is known as free space loss. In open field, you have an antenna out there, and it's broadcasting. The further it goes, the more it spreads out, the weaker the signal gets. Right? That's all we're talking about. FSPL is the greatest form of loss in an RF link. Just free space. CCI, okay? So reflection, right? What was CCI?
Conduct?
Cross-channel interference.
Close, co-channel
Co-channel
interference,
interference.
right? Same channel, too close. Overlapping bands, right? Frequency, what's it measured in?
Hertz.
There you go, cycles per second, right? Hertz. Distance an RF wave travels and the time it takes to make one complete cycle. What was that called? Signified by lambda?
Wavelength.
Wavelength.
Wavelength,
Yeah.
Jesus.
All right, so in review, this is what we covered, right? Radio frequency basics, the definition and understanding of RF, transmitters and receivers, how they communicate, characteristics of RF, including wavelength, frequency, amplitude, phase. Anybody have any questions over those? No? All right, and then coverage and capacity, right? Two of the biggest factors when trying to build out your wireless network. Two important areas ensure wireless deployment will offer reliable connectivity, correct channel reuse to minimize interference, cause and effect of co-channel interference, RF behaviors such as reflection, refraction, absorption, RF units of measure, right? So everything is built out to do in watts, decibels, right? Radio frequency signal measurements, okay? So we're gonna take this information, we're gonna be able to apply what we've learned here and actually get these measurements. That's the goal, right? Take these measurements, figure out how much power we transmit out and how much power we actually receive, right? To be able to do a correct survey. Anybody have any questions as we wrap this lesson up?
Nope.
No?
Nope.
All
Sounds
right,
good.
well, thank you and have a great day.